Hi, this is Professor Jim Chen at California State University, Long Beach. In this video lesson today, we'll look at function evaluations and representations in the context of modeling in abstract symbols. We'll do this through examples. First, let's look at the following. A cell phone plan costs $39 a month. The plan includes 400 free minutes and charges 20 cents for each additional minute of usage. Let's try to model the cost over the usage. Particularly, let's answer part A. Construct a model C for the monthly cost of the plan if the buyer uses X minutes of call time. To answer this question, let's just think about some numbers. How much would you pay if you only call 0 minutes per month? Yes, that's $39. How much would you pay if you use 1 minute? $39. How much would you pay if you use 100 minutes? $39. Well, how much would you pay if you use 500 minutes now? Well, that takes a little bit more thinking. But you notice that there are actually two different types of behavior that you can use to model. That is, as long as you stay within 400 minutes of usage, you only pay $39. As soon as you pass the 400-minute mark, you're going to have to pay $39 plus additional minutes. And then that's going to be 0.2 times each additional minutes beyond the 400. So just think about this. You write this as a C of X, which is the cost. That's a function of the minutes used. And there are two different behaviors. That's we're going to use two different functions to represent it. For the first one, we know it's going to be a fixed cost of $39 if we only use less than or equal to 400 minutes. And that is going to be greater than or equal to 0 minutes because it doesn't make sense to talk about negative minutes. As soon as you pass that 400 mark, that means when X is greater than 400, and we're going to charge the $39 of a fixed cost plus the variable cost of 0.2 times each additional minute. Now let's think about this. If I simply just put down X here, would that actually make sense? Well, this X here is a number that has to be greater than 400. So the first X value you can actually use would be 401, for example. But if you put 401 in this place for X, you get 0.2 times 401, and then plus the $39. That amounts to something a lot bigger than you really want to see. Okay, so to actually fix this, we have to change the value on the X to X minus 400. How does this actually make sense? For example, if X is equal to 401, and you would get 401 minus 400. That's the one additional minute that you use. For that one additional minute, you will multiply it by 0.2 to get that additional charge, which is the 20 cents. This is called a piecewise continuous function. And the domain really matters here. The domain for the first piece is from 0 to 400. And the domain for the second piece is all numbers greater than 400. Next, let's look at what it means to compute C of 100, C of 400, and C of 480. C of 100 takes in the value 100 that is less than 400, which means we should use the first piece to do this evaluation. And the function basically says it's just going to be 39 when X value is less than 400. So we know this is going to be 39 since the X value, which is 100 here, is less than 400. What does this number mean, 39? Well, when the input is 100, the output is 39. That means it costs $39 if only uses 100 minutes of call time. Now try to do C of 400 and C of 480 yourself. Well, C of 400 is fairly straightforward as well. If you simply just replace this by 400, we would still get 39 as the answer because, again, 400 is less than or equal to 400 as it is the domain in the first piece. So we still use the first piece to get the function value, which is 39. And the way we interpret it is very similar. It costs $39 if the user only uses 400 minutes of call time. Now for 480, well, that's a different story because a 480 is actually greater than a 400, which falls in the domain of the second function. So we should actually use the recipe from the second piece to do this calculation. So C of 480 is going to be 39 plus 0.2 times 480 minus 400. And this evaluates out to 39 plus 16, which is 55. So what this means is that it costs $55 if the user uses 480 minutes of call time. Next, let's try to graph this function here. It is a piecewise continuous function, so we expect to have two pieces on this function here. And the breaking point is at the 400 mark. So we're going to first label the 400. And for the first piece, it should follow this of a constant trend of 39 in between 0 and 400. So if we find a 39 on the y-axis, which is the cost axis, C, and then we should just make a flat line or a horizontal line that goes from the 0 points all the way out to 400, and it should include the endpoint here as well. That's called the constant function. Well, the second piece takes a little bit more work. The description for the second piece is given right here, and remember it only works from 400 and on, so we expect to actually start at this point at 400 here. And how do you actually draw it? Just be careful of the scale here. The horizontal scale here is measured by hundreds, but the vertical scales here is measured by maybe in the tens. So let's just maybe graph a couple points here. Let's just say this is 500 and this is at a 600 mark. Okay, I'm going to try to get a point at the 500 mark here. When x is equal to 500, that's when I replace this by 500, I will get 39 plus 0.2 times 100, and that is 59. Let's just try to get another point maybe for 600. So when x is equal to 600, I will get 39 plus 0.2 times 600 minus 400 is 200, and that gives me 79 here. So go over here and grab the point of 500, comma 59. That would be right about here maybe, and grab another point which is 600 for the x, but then 79 for the c. That would be about right there. Okay, now if you connect these points, and hopefully they fall on a straight line here, and they should, you would get this picture. Hypothetically speaking, you would just keep this line going because it doesn't say where this model would stop. So as long as you continue on past the 400 mark, it should follow that linear trend. Next, we're going to look at function evaluations in abstract symbols, and we're going to particularly look at calculations that involve something called the difference quotient. This notion of difference quotient will show up later on in the calculus course. So we want to get ourselves familiar with the calculation that's involved. The difference quotient is defined as the following. If we have a function f, then if we take f of a plus h, and then minus f of a, and then divided by some small quantity of h, where h is assumed to be not equal to 0, then this expression here measures the rate of change for the function f, evaluated at the point a plus h, and the function evaluated at a. For simplicity's sake, I'm just going to denote this as dq for difference quotient. I'm just going to do a few examples to illustrate how to calculate difference quotients on some general functions. For example, if I want to calculate a difference quotient for f of x equals x squared, well, the difference quotient calculation involves getting the f of a first, and then f of a plus h, and then subtract the 2, and then eventually divide it by h. Okay, so let's do this slowly. What is f of a equal to? F of a is to go back to your original function f and then replace x with a. And remember, the function is an action, so this is saying that the action on the input is just to square its input. So I'm just going to take my new input here, which is a, and then square that. Similarly, when I do f of a plus h, the action says to square its input, right? So now the input is a plus h altogether, right? This whole thing is the input, so I'm just going to square that. A lot of the times you actually have to simplify that expression out. So in this case, this is a squaring of two terms, so we can use a formula. The a plus b quantity squared is a squared plus 2ab plus b squared. So we get a squared plus 2 times the first times the second plus the second squared. Next step in the difference quotient then would be to subtract those two things we've just found. So f of a plus h minus f of a, is going to be a squared plus 2ah plus h squared minus the a squared there. Now notice that the a squared actually cancels out. This reduces down to 2ah plus h squared. Now we're ready to actually put it all together into the difference quotient formula. So the difference quotient now is what we've just found here divided by h. Well, that is the same as doing 1 over h times this quantity, 2ah plus h squared. You're going to see this a lot. This h that we have in the front here can oftentimes be canceled out with an h that we get to factor out of here. So I'm just going to factor out an h from the numerator here, so because it's actually common. If you take out an h from the first term, you get 2a left. If you take out an h from the second term here, you get another h left. Because remember, taking things out or factoring things out is equivalent to dividing that term by the term that you factor out. So if you take h squared and factor out an h, that's essentially the same as taking h squared divided by h. So you have another h left. Alright, so now we can write this as 1 over h times this h that we factor out and 2a plus h. So now you see that we can actually cancel out the h over h and left with 2a plus h as our final answer for this difference quotient. Let's do another example. Let's do a very, very interesting and simple example. If f of x is 3, then what is the difference quotient on f? The difference quotient is f of a plus h minus f of a over h. But what is f of a plus h in this case? Action is 3, and basically anything you put into this function will come out of 3 at the end, right? So the action is basically saying just turn it into 3 regardless what your input is. So f of a plus h is going to be 3. F of a is also going to be 3. And if you subtract those two and then divide it by h, we should get 0. Alright, so let's do another one that is a little bit more involved in the computation. Let's say if we want to find a difference quotient for the function f of x that is x over x plus 1. Okay, so let's do this a little bit slowly. Well, first let's figure out what f of a is. Well, let's just replace x with a. Well, what about f of a plus h? Well, that is to replace x with a plus h. So you go back to your expression here and carefully replace everywhere you see an x by a plus h. We should get a plus h divided by a plus h plus 1. Now, we need to do the difference of those two things we just found. Well, it's been a while since we've dealt with subtractions of fractions. You got to be a little bit careful here. Well, let's just rewrite what we've found earlier on. This is a plus h divided by a plus h plus 1 minus a over a plus 1. The denominators in those two expressions are completely different, which means the common denominator should be the product of those two things. So we're just going to write those two terms next to each other because that's the product. And on top, for the first term here, it's missing the term a plus 1 in a common denominator. So I'm going to take my a plus h and then multiply by the a plus 1. For the second term here, it's missing the a plus h plus 1. And it's connected by the minus sign in between here, which makes this a minus sign. And just have a times a plus h plus 1. I'm going to put two dots in the denominator because I'm lazy, and mathematicians use two dots to indicate that things didn't change from one step to the next, just so that we can write a little bit less. On top, we're going to try to simplify it by multiplying those two factors in. So if we do this carefully, term by term, you get a squared plus a, and then plus the h times a, and then plus h. The second portion right here, we're going to be a little bit careful here. We have a negative 1 sign that we need to be careful about. When you distribute a negative a in, you get first negative a squared, and then you have negative a times h, which is negative ah, and then we have negative a times 1, which is negative a. Alright, so now we can simplify this by canceling out like terms on top, and then that's a squares go away. There is an a term to go away, and there's the ah and the ha. They're really the same thing because it's a product of two real numbers. They come out to be the same. So really the only thing left on top is h, and the bottom is still the same. So now the difference quotient is what we've just found there divided by h, and that's going to be h over the a plus h plus 1 times the a plus 1. So again, h can be canceled. All we have left is 1 over the a plus 1 times the a plus h plus 1. And that is it.